Hello everybody and welcome back to another episode of Science with Mr. Emond. Today we're going to be looking at a topic in Chemistry 30 about the solubility product constant, or Ksp. We've already learned a few things that are going to be helpful here, specifically about the equilibrium constant expression, Keq. Ksp is going to be a little bit different because it deals with when ionic compounds are actually going to be dissolving. And that's the kind of key difference here. And we already know from previous courses like Physical Science 20 that when ionic compounds dissociate, they do so into their separate ions. And that's going to become pretty important here. We're going to review dissociation equations quickly. Here's an example of one where you have silver chloride, which is a solid, and it's going to dissociate into silver 1 plus, which is its charge. This is a positive ion, otherwise known as a cation, and it's also going to dissociate into chlorine minus. So the AgCl is going to split up into its positive and negative ions. Now, just to review, what is an ion? This is an ion. This is also an ion. This one is a positive ion, known as a cation. This one is a negative ion, known as an anion. Cations and anions are ions. Ions are things that have charges. So they're atoms with charges, meaning they've gained or lost electrons. This is all a review. When we talk about something called dissociation, what we mean is when a solid ionic compound is being added to water and therefore becoming aqueous. When that happens, the ionic compound tends to break down into its separate parts. So in this one, the AgCl is breaking into its parts, which are silver, which is a positive 1 cation, and chlorine, which in this case is a -1 negative anion. All right. So let's kind of narrow in a little bit on our definition of Ksp. When we're looking at Ksp, which is the solubility product constant, we're going to be focusing on compounds that have what we call low solubility. And that's, of course, in water. So we've been using for a few years now a solubility table. And in that solubility table, when we've seen the word low solubility, we've been assigning it a state of solid. That same table is what we're going to be using here. And low solubility compounds that you've been finding in previous units already are what we're going to be focusing on here. So, in every example that we do, we're going to consider a saturated solution of the insoluble substance that's in contact with some kind of undissolved solid. And the important things to remember here are, first off, some of the solid actually does dissolve. Just because it's low solubility does not mean that it doesn't dissolve. It just doesn't dissolve well. Some of that solid is dissolving. And when something dissolves, the substance dissociates. And the third point, if something is dissolving, we know that there is going to be an equilibrium between the two states, between the undissolved solid or the reactants, and there's going to be a balance between those undissolved solids and the dissolved ions. And so that's important to remember. When you set up the Ksp expression, it actually looks almost identical to the Keq. So the first step of this is to set up your dissociation equation. And so I've done that here for you guys. And I mean, this is exactly like what it looked like on the previous slide. And then step 2 is, well, you set up the Ksp expression, which is not a big deal, right? You only have a few rules. do not include solids or liquids. And that's the same as the rules for the KEQ expression. So nothing much has changed. And instead of writing KEQ, yes, we are dealing with equilibrium, but this time we're dealing with the equilibrium of things that have low solubility, so we say Ksp. Don't write KEQ for things that have low solubility. And what you're going to notice is, in general, when we are dealing with things that have low solubility, they're going to be a solid, right? And the things on the other side that they dissociate into are aqueous. And so when you set up your Ksp expressions, it actually works out really nicely where you are not going to have anything on the left-hand side. You're just going to have your ions there on the right. So what does Ksp tell us? Well, it tells us a few different things. It tells us the solubility of our substance, how soluble it is. And from it, we can learn what the ion concentrations we have are. So these are the two important bits of information that we can get from our Ksp expression. For that reason, it's important to know how to write these expressions. So we're going to do a couple examples here. And I have the first one done for you. So you have this Ksp value. The solid's not going to be included. And of course, we do products over reactants. So our first product is SN2+. So it's going to be the concentration of SN2+. And then on this side, we have OH-. So we're going to multiply that by the concentration of OH-. Just like with our KEQs, your coefficients in front of your ions become your exponents. So that's where this exponent of 2 came from. What exponent exists here? Well, that's a 1. And where did that come from? From in front of the SN2+. So that's it. Why are we not dividing it by the concentration of our reactants? Because they're solids. Solids and liquids are not included. So let's quickly try these ones out. Our Ksp for this one is going to be equal to the concentration of our Ag+, and it's to the power of 2, multiplied by our concentration of this. So this is CrO4, 2-, and what power does it have? There's a 1 there, right? So we could write the 1. Is it necessary to write 1s? No. So I'm just going to go ahead and erase that. I just wanted to show you it's there, but we don't have to write it. And finally, give this one a shot. So we have our Ksp is equal to our concentration of iron, 3+, multiplied by our concentration of OH-, but this concentration is going to be to the power of 3. And there we go. We've done some examples here for Ksp. Let's try doing some calculations. So now we're going to work on calculations using our Ksp expression. And these are going to have steps just like everything we do in science, right? The first step is simple. Write the dissociation equation. That's it. So we're going to start with that, writing dissociation equations. And we're going to make sure that we balance. So before we move on to the next steps, let's actually do this with an example. All right. Example 1, calculating the Ksp. So here we have the concentration of lead ions. So lead is Pb, and it's in a saturated solution of PbI2. So we want to know what the solubility constant is. So we're going to start off with, like we said before, writing the dissociation equation and balancing. So we have PbI2, and this happens to be a solid. And it's going to dissociate in water into Pb2+ and iodine minus. Now what happens here? We have to balance it, right? How many Pb's are on the left? 1 on the right, 1. 2 iodines on the left, 1 on the right. So this needs to have a 2. And just for good measure, let's put our other coefficients there. Now the whole reason we did that is so that we could do this next step. Step 2 is to write out your Ksp expression. So let's try that out. In this case, our Ksp is equal to the concentration of Pb2 plus to the power of 1 multiplied by the concentration of iodine negative to the power of 2. Step 3 says use stoichiometry to find the concentration of your ions, and use the concentration given to find out the concentration of the ion you want to find. So this actually is going to be simpler than you think. We need to know these values. We need to know the leading coefficients for this. So I know that the concentration of my lead ions, which is this one right here, is 1.3 times 10 to the negative 3. So I know this one is 1.3 times 10 to the minus 3 molarity. Do I know the concentration of iodine? I actually do here, because what do I know about the ratios of lead to iodine? I know that for every 1 lead, I have 2 iodines, which means if I have a concentration of 1.3 times 10 to the 3 lead ions, then I'm going to have twice as many iodine ions because they're a 1 to 2 ratio. So I can just go ahead and do that right here. I don't really need a calculator because 1.3 times 2 is 2.6, and that's of course going to be times 10 to the negative 3. And there I go. I have my 2 concentrations, and I don't want to forget that this one's squared. At this point, you know, you're in the home stretch. You're going to be working on step 4. And step 4, we kind of already did it because it's just that easy. You plug the values that you found into the Ksp expression and you solve for that value. So we already kind of did step 4 here, which is plug them into our Ksp expression. Now we just need to solve for them. So we take out our old trusted calculator here, and you type in 1.3 times 10 to the negative 3. And you're going to multiply that by 2.6 times 10 to the negative 3. But that is going to be squared. And we get this, remember we only want 2 sig figs here, so 8.8 times 10 to the negative 9. So our Ksp value is going to be 8.8 times 10 to the negative 9. And we are going to be done with that one. As easy as that. All right, so let's go ahead and try this out again. Another example. And we're going to try to do this just from memory this time because we've done one with the steps already. So step 1 is to create your equation and disassociate, right? And balance. So we have the Ksp for MgCO3 is 2 times 10 to the negative 8. What are the ion concentrations? All right, what do I know? I know that I have MgCO3, and that's a solid. And that when you put that in water, it's going to disassociate into Mg and CO3. Now, I need to look these up, right? I know that Mg is 2 plus, and CO3 is 2 minus, and that's why over here they have a 1 coefficient on them. Do I need to balance this? It looks like it's already balanced, so these are all 1s. So that's kind of nice. There, I have the balanced, and I have my coefficients. Now, I know the concentration for this is... Actually, no, I don't. That's not the concentration. That's the Ksp. So I know that the Ksp is equal to my concentration of magnesium multiplied by my concentration of CO3 2 minus. That's what I know. And I also happen to know that the Ksp is this. So I know 2.0 times 10 to the negative 8 is equal to these things. And I need to find the ion concentration, so I need to know what these are. So you might think, oh no, I'm stuck. But you're really not, because what you do know is whatever the concentration of magnesium is, whatever this is, the concentration of carbonate's exactly the same. And how do I know that? Because they're 1-to-1 ratios. So they have to have the same concentration. Now, if they have the same concentration and we don't know what that is, we can call the concentration of magnesium X, and we can also call the concentration of carbonate X. And X times X is X squared. And that's equal to 2 times 10 to the negative 8. So as long as you know the ratios, you're going to be fine, right? It's 1-to-1, X squared. How do I solve for X here? I need to take the square root of both sides. Now we know when you take the square root of something, you're going to have plus or minus, but we're dealing with ions here. You can't have a negative amount of ions, so we're only going to work with the positive value. And at this point, you just need to toss this into your calculator. So I have 2.0 times 10 to the negative 8, 2.0 times 10 to the negative 8. And this value, we need to square root it. And we get that. That looks like, I want 2 sig figs again, so 1.4 times 10 to the 1.4 times 10 to the negative 4. So X is equal to 1.4 times 10 to the negative 4. Now we're not done. We solve for X. We know that each of these are X, so I'm going to write my answer out a little bit better here. The concentration of magnesium ions is going to be 1.4 times 10 to the negative 4. And the concentration of my carbonate ions are also going to be 1.4 times 10 to the negative 4. I solved them both. So there we go. I have the concentrations of my ions. All that's left is to box my answer. And that's it. That was kind of easy because they were in a 1-to-1 ratio. So what happens when it's not in a 1-to-1 ratio? Let's give something like that a shot. The steps are going to be kind of similar. So we have silver 1 chromate. Silver is Ag. Chromate is CrO4. Now, silver, we're saying, has a charge of 1, so there's only going to be 1 chromate, but I believe that CrO4 has a charge of 2-, so it's going to be Ag2CrO4. And that's going to break into 2 Ags and 1 chromate, which has a charge of 2-. Of course, this is solid, and these are aqueous. So I have my balanced dissociation reaction, which means I can write my Ksp expression, which is going to be the concentration of silver to the power of 2 multiplied by the concentration of my chromate. There we go. I also know the Ksp is 1.1 times 10 to the negative 12. So this values that. Do I know my concentrations? Not really, right? What do I know? I know that I have 2 more Ags than Cr4s. So if I call X the concentration of CrO4, I know that I have 2 more silvers than that. So my concentration of silver is going to be double that, or 2x, right? If CrO4 is X, then because I have twice as much silver as I do chromate, then I have 2x concentration of silver. But this one's squared, and this one's to the power of 1. So again, we just keep going. 1.1 times 10 to the negative 12 equals, what's 2x squared? That would be 4x squared. And we need to multiply that by x. What is this? Well, 4x squared times x is 4x cubed. What do we do now? We need to isolate our variable. So let's divide everything by 4. At this point, I think we're going to need a calculator. So we're going to have x cubed equals. Let's take out our trusty calculator. And we need to do 1.1 times 10 to the negative 12. 1.1 times 10 to the negative 12. And this we need to divide by 4. And that's 2.75 times 10 to the negative 3. 2.75 times 10 to the negative 3. How do we get rid of this cube here? Well, the same way we got rid of the square. And the way we do that is we take not the square root, but the cube root. And we have to do that to both sides. So we're going to cube root this time. So we're going to modify our root to be the cube root. And here we're going to put our answer, which is 2.75 times 10 to the negative 13. And that is 6.5 times 10 to the 1, 2, 3, 4, 5. 6.5 times 10 to the negative 5. So x is 6.5 times 10 to the negative 5. Molarity. All right, we need concentrations. It doesn't really ask us for that, actually. It's not. Calculate the molar concentration of silver 1 chromate. Okay, well, let's just do the concentrations of everything, just because we only need to give this one, but we're practicing here. So the concentration of chromate is x, right? And we solved for x. What is that? 6.5 times 10 to the negative 5. All right. Silver, we have twice as much as. So we need to double our answer. So 2 times our answer is 1.3. And the reason why I'm doing this is because our exponent's going to change. 1.3 times 10 to the 1, 2, 3, 4. See? So the concentration of Ag, why did I put a 2 there? I don't know. Concentration of Ag plus is 1.3 times 10 to the negative 4. And of course, these are molarities. What's the concentration of our silver chromate? Well, this is a 1. So silver chromate and chromate are a 1-to-1 ratio, so it's going to have the same concentration as chromate. So you can see we really didn't need to do much other than that, but just for practice sake, wanted to show you how it's done. So there we have all the ion concentrations. That's going to be it for this video on how to use your Ksp expressions and how to find your ion concentrations through stoichiometry and balancing your dissociation equations. See you next time. Bye-bye.
Thanks for watching, everybody. You can like, follow, and subscribe to my social medias to get notifications as soon as new content is uploaded. In the top corner here, you will find the playlist that this video is in. Watch the unit from beginning to end, and over here, you will find the next video in this unit. Keep learning, everybody. Take care.